Okay, good morning. So we will continue with one more problem on solid angle, then we will go on to radiation pressure. So you can just hold on to that, you do not have to copy that now, I will give you time. So problem number 4, determine the fraction of the total, problem number 4, determine the fraction of the total hemispherical emissive power. Determine the fraction of the total hemispherical emissive power within brackets you can write E in watts per meter square, right, to make it clear, within brackets capital E in watts per meter square. So determine the fraction of the total hemispherical emissive power within brackets capital E watts per meter square, leaving a diffuse radiator, in the directions in the direction 0 less than equal to theta less than equal to 60 degrees and 0 less than equal to phi less than equal to 45 degrees. Can you solve? Yeah, please go ahead. So for a diffuse radiator, I lambda E is not a function of theta and lambda, that can be pulled out. So you assume that one integration with respect to lambda is already done, right. So E is correct. So what is E fraction? Okay, you want that fraction. So I lambda E can be taken out, I can be taken out. So what is this one? 45 is pi by 4, okay. Is it okay, Vikram? Okay, what is that, cos theta sin theta is sin 2 theta by 2, okay, minus cos 2 theta by 2, how much is it? No, tell me that, into this is 3 by 8, huh? Oh, okay. By 32, huh? So therefore E fraction by E is 3 by 32, huh? okay. The most important point you have to recognize is out of 0 to 90 you have 0 to 60, that is 2/3, okay, that is 2/3. Out of 0 to 2 pi you have 0 to 45, how much is it? 1/8. So what is the product of these two? 1/8 into 2/3, 0 to 60, how much of, what is the fraction as opposed to 0 to 90? You appreciate the logic. What is that fraction? 1/12. But do not do some shortcuts like the 60 degrees divided by 90 degrees into 45 degrees divided by 360 degrees. That sin theta cos theta d theta, that is because of the area, okay. So it is a non-linear function, it is a trigonometric function, it is a function of sin theta cos theta. Therefore if you want to find out what is the radiation going out in a particular direction, there is no other shortcut, sin theta cos theta d theta d phi you have to integrate. Fortunately there is a diffuse radiator. Suppose I give you a problem in which I lambda e is equal to 3.5 cos theta into sin phi minus 4.6 tan theta into cos squared phi, something like that, you are sunk, you will keep on integrating for half an hour. But whether such a surface exists is another matter, but as a prof I can always give some problem like that and give trouble to you. So what I am saying is, if it is diffuse the story is very nice, and if it is azimuthally independent, lot of bother is solved because 2 pi you can take out, generally it is the case, but zenith angle dependence will usually be there, particularly for solar applications and all that, that is it will be a function of theta. So during this course somewhere down the line we will try to look at problems where I is also a function of theta, so that you get some exposure, you get some experience in solving problems in which the directional dependence is not completely wiped out, okay. Now so these are basically the preliminaries, the basic grammar which is required to understand radiation properties of a black body. Now we have set out to explore, okay, what that I is, okay. Yesterday we asked that question, so it begs the question, what is I? We do not know if I is given, if it is diffuse we can do all these things, we can find out what is a fraction, or between two bodies if E is given and if it is diffuse I can put the E equal to pi IB, I can do all that and find out what is the heat flux which is coming on the second surface, if you know what is the emission from the first surface and so on. But suppose I know only the temperature of the first surface, from the temperature how do I get E or I is something which I do not know as yet. This comes from basic radiation laws which we will have to figure out, okay. So the first important concept in that is the concept of radiation pressure, okay. Radiation also exerts a pressure. This was something which was unknown till 1876, okay. This was known for this was known before also, but it was the Italian physicist A. Bartoli in 1876 who first proposed a thought experiment to prove the existence of radiation pressure, okay. So his apparatus is like this. So this is A, so this is A. Bartoli's thought experiment, he is an Italian physicist. This is the top view, so please remember so this is the top view of the Bartoli's thought experiment. It is a cylindrical chamber, okay. So it is a cylindrical chamber which is insulated on its periphery, so it is like this, okay. So I am not allowed to go, but anyway I think you can't take it, okay. So the side view it is like this, no, the side view will not come next to the top view, isn't it? Anyway, so I am trying to say that it is like this, if you view it from the side it's a cylinder, okay, forget about that. So the ED pros will forgive me for doing such things, okay. So the story is like this. So you have a cylinder, you have vacuum inside, okay, not necessarily vacuum, we will see it is filled with radiation corresponding to radiation and energy density which corresponds to black body at a particular temperature. Let us come to that story. Now this is a cylindrical chamber, it is insulated on both sides so that there is no convection or any other heat loss, okay. It is attached to a black body on the left hand side, the black body is at a temperature T1. It is attached to a black body at T2 on the right hand side, okay. T1 is less than T2. Okay. There are two movable pistons, okay. There are two movable pistons 1 and 2 which are contained in this cylindrical enclosure. This movable piston have a small gap in between, okay. There is a small gap in between which can be covered or opened by sliding valves. That means the valves can be slid open, that is the valve can go, this valve can go up and down, this valve can go up and down, this piston can move, the pistons are frictionless and they are perfectly reflecting, all these are perfectly reflecting. Now Bartoli proposed a thermodynamic cycle with this, okay. He never made this, experimental setup, but he proposed it is thermodynamically correct, so we accept it as truth, right. So he postulated a thermodynamic cycle. So cycle with 3 processes, okay. So watch carefully, I am not going to write everything on the board, you have to hear and as and when I say an important point you can jot it down. The first process is the valve which is close to this piston 1 is open, watch carefully, the valve which is close to the piston 1, okay, is open, this valve is closed, okay, and this whole thing, this container, this portion of the container is in thermal contact with the black body at T1, that is it is contact with the black body at the left hand side. You give enough time such that cavity, okay, which is extending up to the piston 2 is filled with radiation energy density corresponding to the black body at T1. What that energy density, I is a function of temperature, but what that function we do not know, but we can now say that if you give sufficient length of time, and these are basically all these are non-conducting and all that, right. This also, this insulated, is perfectly reflecting, okay. So this is closed, this is open, so now this whole this chamber A and B, we can take 3 chambers, A and B are now filled with radiation corresponding to black body radiation at a temperature T1 in Kelvin, okay. Now process 1, the valve near piston 1 is closed and the piston 1 moves, the piston 1 moves towards B, piston 2, till such time the radiation energy density between the 2 pistons rises to a value corresponding to a black body temperature at T2. It is a hypothetical cycle. he considers that it is like compression, okay, it is like you are compressing a gas or whatever, okay. I will come to the story is very clear, you just listen to it and finally it will all be clear. So this is closed first, this is open and you allow enough time so that these chambers A and B are filled with radiation energy density corresponding to a black body at T1. Now this red valve is slid open, okay, this red valve is slid, this red valve is closed and then it is moving towards this such that this area becomes less, so the volume becomes less, therefore the radiation energy density increases to a value corresponding to a black body at T2. Now anyway this fellow is in contact, the chamber C is in contact with the black body at T2, therefore the radiation energy density corresponding to the chamber C will be the same as the black body at temperature T2. Now what happens is this is slid open, now the new position of this is here, the new position is here. What is the radiation energy density corresponding? T2. What is the radiation energy density corresponding to this? Now you open this, so everything is and then this is moved towards this and everything is moved towards T2 such that radiation energy density is pushed, that everything is pushed to the black body at T2. Now the third position, the third process of the cycle is bring it back to position 1, okay. Now in this hypothetical cycle everything is alright, okay, everything is alright except that you RG'd the second law of thermodynamics by transferring heat from a body at lower temperature to a body at higher temperature. That heat could be radiation, conduction or convection, in this case it happened to be radiation. Now while it is forbidden by the second law of thermodynamics, it is allowed provided extra work is done. Therefore you have to find some mechanism, you have to find a place where this work could have been done. Where could this work have been done? Pushing the so it could, in step 2 when you are pushing it from T1 to T2, work could have been done. Who will receive the work? Somebody has to receive the work, or it has to come. I told you that the piston is frictionless, so frictional work generates heat and then you can raise the temperature by T1 to T2. The valves are frictionless, the pistons are frictionless, everything is frictionless, but if heat transfer has to take place from body at lower temperature T1 to a body at high temperature T2, some work should have been done. So Bartoli argued, if everything is correct and second law of thermodynamics has to be obeyed, this work must have been done against the radiation pressure. Therefore radiation can be treated like a gas, so when you are moving it from T1 to T2 you do work and compress it. This is the only way by which this cycle will work and there is nothing wrong in the cycle, therefore radiation pressure exists, okay. It is slightly shady, but among all the proofs this is the best, that radiation pressure exists. People have measured radiation pressure, it requires high precision, it is not a fantasy. People have put large sails and found out, you cut out the wind component and this, and you can have a sailing boat based on radiation pressure and all that. It is possible, but you have to have huge sails and all. So radiation pressure is not a fiction, it is very small and it is very difficult to measure it. So Bartoli in 1876 proposed hypothesis based on thermodynamics, okay. So if you have to compress it from T1 to T2, that is the radiation energy density of the gas changes from that corresponding to a black body at T1 to that corresponding to black body at T2, radiation pressure is assumed to exist. Therefore it opens up new vistas for doing research, because for exploring because basic thermodynamic laws are applicable to radiation. you can assume that the radiation has a pressure. If you assume that radiation also has an internal energy or the radiation energy density, this pressure and energy density, if you are able to relate it to I, and then pressure and internal energies can be worked out using TdS relations, TdS equal to du plus PdV, TdS is dH minus PdV, you can play with all thermodynamics and you can come up to a particular level. So it just opened up vistas for analyzing for the quest of this I. So this opened up some new vistas in the pursuit of what is a correct distribution for I, okay. So but you can see that thermodynamics can go only thermodynamics can go only to a certain extent, it can go only this far, that is it will help you get the averaged out quantities, but I lambda as a function of lambda thermodynamics will not be able to give you, that we will see, okay. Now what is the mathematical expression for the radiation pressure? Now in the next 3-4 classes we will go through very slippery mathematical derivations, so please pay attention. So after the class when you go back to your hostel you can write down process 1, 2, 3 and this thing, I am not giving you time, it becomes boring if I write it on the board and I hate using PowerPoint, okay. So now we have to really go through some tricky mathematical derivations. Radiation pressure, now let us consider same this coordinate system and the dA1 will haunt you throughout the semester, okay. R theta phi dA1 is the emitting area, so what is our favorite in thermodynamics? Just like I put x, y, z, dA, theta phi, piston cylinder arrangement. So the piston cylinder arrangement is a basic, the favorite example with which we can develop our ideas. Now, okay, so dA1 is dA is the emitting area. Let us not worry about dA1. I have to write dA1 only if there is another area dA2. Why unnecessarily I have to make matters worse by putting 1 and then after 4 steps I may forget that subscript and all that, I will land in trouble. Let us leave the dA1, we will call it dA. So radiant power passing through so this is very compact notation for saying theta phi direction, you can put it in brackets. What is this? What is the radiation power passing through dA? I lambda E into what is that story? So dq lambda theta phi is equal to I lambda E dA cos theta d omega, correct, good. So d lambda, this is nothing new. No, that we can worry later. Radiant power passing through, we can, it is a radiation energy density corresponding to that. If you want you can take it like that, but yeah, radiant power on it, okay, radiant power which is coming onto it. Now what is the net momentum flux passing through dA? What is the net momentum flux? Now this is pretty tricky to answer. I can relate the momentum flux to the pressure, okay, but I need to have from this radiant power I should be in a position to relate the radiant power to the net momentum flux. How can I do that? Let us look at this. What are the units of the radiant power? What are the units of radiant power? Watts, no problem, right? What are the units of this? Area is dA, speed is the speed at which radiation propagates. What is the unit of this? Meter cube per second. I have a power in the Newton in the numerator. No, what will be the unit? Watt. Watt per meter squared. Meter second. What is the watt second? Joules per meter cube. Thermodynamically, what joule represents what? Energy. Energy divided by meter cube can represent energy density. How can I write joule in terms of Newton? What is this? Newton per meter square is what? Pressure. And who proposed that radiation as a pressure? Bartoli. So all these guys, hook or crook, they are trying to get some expression for radiation pressure. Don't worry about it, everything is correct because it can be verified by experiment. Okay, because you're getting exposed to all these concepts for the first time, it is difficult for you to understand, but these are all correct. Okay, so the net momentum flux can be figured out by taking the radiant power and dividing it by area into the speed. Okay, can you do that now? So can I say d psi of two? Okay, you are convinced that it has got the units of joules per meter cube or Newton per meter square. So if we proceed along this direction, we should get an expression for radiation pressure. That is the goal of this exercise. The title is radiation pressure for this subsection. So by doing this mathematical derivation, by going through these steps, we should be in a position to get an expression for the radiation pressure. What are we trying to do in this? Or at least relate I to pressure. See, it is something like I is the only thing I know, but with I am not able to proceed further. Through my fundamental geometry like solid geometry and definition of spherical coordinate system, if you give I can find so many things. What is the, how much will the second surface receive, what is the orientation, how much will be the fraction of energy in a particular direction, all those things I can find out. But given a temperature, what is I, that question is not answered, that is more fundamental. So many people, so many physicists in the last 150 years from 1850, from 1800 to 1920, they were trying to find some expression for I. Some thought by just using plain thermodynamics they can get. Some people thought by using classical physics, that is kinetic energy, kinetic theory of gases and all that, they can get. But none of this worked out, and eventually a new hypothesis called the quantum hypothesis has to be figured out. Now we are seeing the first part. There are three parts to the story: A, B, C. A is based on thermodynamics, B is based on classical theory, and C is the actual quantum hypothesis. As far as A is concerned, you can get to a position where you can say I is proportional to t to the power of something, that is all. But how varies with lambda cannot be obtained from, it is beyond the scope of thermodynamics. But to put things in perspective, we have to proceed from thermodynamics. So basically we are trying to get an expression for I, and if I know I can do all these calculations. but now I have no way to, I have to start somewhere. Suppose thermodynamics, I feel that thermodynamics is the tool with which everything can be solved. If I am able to relate I to energy density, I to pressure and all that, then I will assume radiation to be an ideal gas. If I assume radiation to be an ideal gas, then I use Maxwell relation, TdS relations, and I can get some. That is the approach people have taken. That is what we are, that's what we are trying to chronicle now. Whatever those so many great physicists, their lifetimes work, we are doing in 20 minutes, 30 minutes, 40 minutes. Okay. Now, so my goal is left hand side is, left hand side what are the units? Newton per meter square pressure. Right hand side I am getting dq, but already in the expression 1 dq is written in terms of I. So if I complete this exercise, I will say that radiation pressure is some function of, radiation pressure is some function of I. If I know that, I will keep it. Then what is radiation energy density as a function of I will keep it. Now I will say radiation energy density is like any other energy density or internal energy. Now if I have expression for both u and p, then I will go to the expression TdS is du plus PdV, and then I will use all my thermodynamic, I will manipulate and then try to get something. So that is the goal. So first we have to get an expression, or I need not say all this. Suppose I say P is equal to 4 pi I B by 3 C or something, you will all be flummoxed, you won't know how these expressions have come. Therefore this becomes inevitable, these derivations are inevitable. Now this is expression number 2. Now what is a component normal to the radiation? Component normal to dA, right? That is very important, isn't it? What is a component which is normal to dA? Because it is going in this direction, isn't it? Or it is coming in that direction. What is the direction? What is the component normal to dA? There will be a cos theta, right? Therefore d psi n cos theta. I think this gives you a, as Vinay had a problem, we will remove the E, that makes it clear, right? Because A is receiving the radiation, right? dA is receiving the radiation, we will keep it as I lambda instead of I lambda E, right? So I lambda into cos square theta C, okay, fine. Now I am going to tell you something which is controversial, but you will have to accept. If dA is perfectly, what is the argument? If dA is perfectly reflecting, it is just like from a nozzle, you have high velocity water which is impacting the Pelton wheel turbine blade. So the net change in momentum will be what is going in minus what is coming out. Now if dA is a perfect reflector, whatever is going in must equal to whatever is coming out. Therefore the net change in the flux will be equal to twice the value which is obtained in equation 4. You have used these arguments in turbo machinery also, okay. Therefore P is given by 2 by C okay. All right. What happened to the dA? dA got cancelled because I divided na radiant power divided by C into dA, okay. So did you follow this argument? So if you have to get the net pressure, this is the elemental change of elemental rate of momentum flux, okay. This has to undergo 3 integrations, one integration with respect to theta, one integration with respect to theta, one integration with respect to phi, and one integration with respect to lambda. But if you do that, this answer is only half correct, because I am saying that it is a perfect reflector, whatever is coming and whatever is going out. If you want to find out what is the net momentum change, incoming minus outgoing, incoming is x, outgoing is minus x, so it is x minus minus x, it will be equal to 2x, okay, that is given by this. Now if for a black body, so P, yes sure, cos squared, okay. Now this will be given by P by 2C, and we can do the, for the black body we can do the IB (0 to 2 pi), I can do the 2 pi also, right, cos squared theta. So people who are not able to, I have done several things in between 4 and 5, I have done several things. First, I have gotten rid of the integration with respect to lambda by saying that I lambda d lambda integral is just replaced by IB. IB is not a function of theta b, because we are assuming that everything is black body, so that is pulled out, point number 1. Second, I already did my integration with respect to d phi, because I is anyway independent, I multiplied 2 pi. So I have done an integration with respect to phi, I have done an integration with respect to lambda, but only thing, this fellow is still, now I have to remove this, right, I have to do the integration with respect to theta, correct. Can you do that? Okay, or so this will be from cos of pi by 2 all right. So it is an important step thermodynamics is achieved 100 years 150 years back, when they related the radiation pressure to the intensity. Okay. The next step is also equally confusing, that is you have to define an expression for energy density. Radiation energy density is U, it is like internal energy joules per meter cube. So we need a figure for this. I will start from here. Same coordinate system, same dA, everything is the same, but now I will make dA like this. Okay. Sorry, this will be, so this will be phi. What is this angle? Theta, good, okay. So some I lambda is falling on this. Okay. Now radiation energy density is, we are talking about something joules per meter cube, but radiation flux in all, radiation power is all watts or watts per meter square. So between the radiation flux or radiation power in watts or watts per meter square, if you have to convert to joules, what is the additional variable which will enter the problem? Time. So therefore you have to consider a time dt. In a time dt, when radiation is shining on an object, how much of energy will it accumulate? Suppose you imagine that this so dl is the swept length in an interval of time dt. What will be the dl if the velocity of radiation, velocity of light is of radiation is c dt. So dl is c dt, that is the, so I am going to do like this. I know what is the radiant power, okay, radiant power multiplied by the time will give the total radiant energy, the power into area and whatever, I will do that. I will divide it by the volume, okay. So numerator I will have joules, denominator I will have meter cube, and I will call that as radiation energy density. But once I have radiant power on the right hand side, the radiant power inherently has I lambda. So on the right hand side I will continue to have I, on the left hand side I will have U. Therefore now I get an expression for the internal energy as a function of I. 10 minutes back I got a relationship between pressure and I. So therefore with pressure and internal energy I can keep on working, and if I get a relationship, finally I can put all this in terms of I and get I as a function of temperature, because I am able to exploit TdS is Pu plus du plus Pdv. So temperature I am bringing. So I can put the crucial link between I and temperature by doing all this Jamela. Yeah. No, we have to always consider radiation is coming like this, we have to consider the area which is like this, because I is based on the projected area.
But the cos theta is in the numerator, not the denominator where the dA is. dA is in the denominator, but we took the cos theta.
No, what did we do? No, the first one was a dA cos theta, we already, that will come here. No, there is no problem in what I have done. It will be a cos theta component, we cannot divide it by cos theta. When do you divide by cos theta?
No, if you say it is because of dA, and dA is the denominator, then cos theta will also be the denominator. It was not because of area.
We are taking component of,
No, we are taking flux. The component of the flux. You already divided by dA in the first place. You divided by dA, Vikram, and finally you got an expression for flux. The flux you can resolve the flux and have a component in whatever direction you want. Now you are having the component in the theta phi direction, okay. Now I think you are the next class, isn't it? Okay, so swept volume. dV equal to dl okay. So I think there is a small change, so you should draw the swept volume based on what? Based on dA cos theta, not dA, okay. So the swept volume is dl dA cos theta. Now total amount of energy is dE lambda, d, what is this? I lambda E, I am leaving that lambda theta phi, please, to save time. Correct? Therefore, is that correct? What? Which one? No, there is no problem. This is what? What will be the units for this in brackets? Watts multiplied by time, joules. What are the units of E? Joules. So numerator is joules, denominator is meter cube. Now can we do this? dl is C, dt, dA cos theta. So correct? Alright, so that is basically now 9, 10, 11. For a black body, watch out, I use 4 pi because I am not looking at a surface, I am looking at a, it can receive radiation from all over the place. I am not taking radiation heat transfer between one surface to another surface, from the top of one surface to the top of other surface. Are you getting the point? But so the 4 pi will come. Therefore, so 11, 12, so the major progress we achieved in this class is we got an expression for the radiation pressure in terms of the intensity, we got an expression for the radiant energy density in terms of the intensity, and finally we got a very crucial relationship that the radiation pressure is basically the radiation energy density divided by 3. So now I will give you a sneak peek of what we are going to do in the next class. The radiant energy, the total internal energy U is equal to the internal energy per kilogram or internal energy per volume into volume, right. Capital U is small u into V, okay. Therefore, when you take the U d of capital U, it is U dV plus V du, that is there. Now TDS is basically equal to Tu plus PdV, that comes from thermodynamics. Now in the du, U is written as a product of small u into V, and P can also be written in terms of U, and P can also be written in terms of U now, is equal to U by 3. Now I will say that radiation is assumed to be a gas which is having a temperature which is having a corresponding to a volume V. and therefore all the thermodynamic laws are applicable, and if I have the TdS relationship, and then TdS must be equal to an exact differential because entropy is a property. Therefore dou by dou y, suppose you have an expression dz equal to m dx plus n dy, dou m by dou y is equal to dou n by dou x. Therefore I can take dou by dou t of the first term equal to dou by dou v of the second term depending on how it comes, and then finally I will get internal energy is nothing but sigma into t to the power of 4, that will come out. But what that I is at a function as a function of lambda specifically between 4.5 micrometer and 4.6 micrometer, what is I lambda, you cannot, thermodynamics cannot answer. But for the complete wavelength interval lambda is equal to 0 to infinity, all the angles are taken into account, you tell me the temperature, I can tell you what is a black body hemispherical emissive power. That is okay for engineering applications, but suppose you are interested in solar energy, in this thing you are doing some applications, and you want to have selective absorbers and selective reflectors, this knowledge is no good, it is not adequate. Okay. So the next class, first 20-30 minutes I will just give you the final result, Stefan Boltzmann's law, actually we can proceed with that, but what is that I, for that quantum mechanical considerations have to be brought in. So the next 3 classes we will work out the quantum mech, how Planck and others derived this. So we are getting Hajar holidays in the subsequent week, okay, and when is the Sarang inauguration? 5 o'clock, right, on 25th. So to cut a long story short, next Tuesday we will have a class 5 o'clock. Yeah, that is what I told you. Suppose I have on 25th, you will say the inauguration is there, you are going home. 18th shall we have the class? 5 to 6 reserve, lab cannot go beyond 5. No, but you say class is there, it is a official slot. You come 5-10 minutes late, I will allow you, you can come through this door. Okay, because there is no other, it is now a heterogeneous class. Alright.